I'll do is I'll go into Shanice's bio, and then I'll ask the technical team to load up her presentation because I don't see her in the room. So I'm assuming that Shanice is going to be not present, but we do have a recording of her presentation. So let me just tell you who Shanice is. Shanice Martin is a recent graduate of a Master of Science degree in Renewable Energy Management with distinction from the Department of Physics at the University of the West Indies, Mona. She has a background in chemistry, attaining a first degree in general chemistry, and always had a passion for environmental chemistry, environmental physics, and conservation. Shanice is a conservation scientist employed in the public sector, and she studies at UWI Mona campus. Today, her presentation is a deep dive into thermoelectric ocean thermal energy conversion and the feasibility of implementing OTEC in Jamaica. So I'm gonna ask the technical team to load Shanice's presentation, or message me if that's not possible, right?
Just a few minutes. I think I need a few seconds.
No problem. Thank you. A great job, Kiani. Dr. Chadee, since we're waiting on this presentation to load, did you have any comments or questions for the first two speakers?
Actually, I just wanted to ask the audience if they have any questions for Kiani. I saw one for Lenica, but I didn't see one for Kiani as yet. So just to
Right,
just
so
trying
ask them to
to
load
thank the
those for
audience.
us. Sounds good. So please feel free to start loading questions into the chat because Dr. Chidi is looking at the chat and pulling out questions. I see our tech team is ready with Shanice's presentation, so we can jump in.
My name is Shanice Martin, and my presentation is on the exploration of ocean thermal energy technologies, shortened as OTEC, specifically thermoelectric OTEC, and its viability as a source of renewable energy in Jamaica and in the Caribbean. Two specific objectives I wanted to capture look on what makes it relevant to the region and how can we improve thermoelectric OTEC through the materials
Team, is there a way for you
in the
to raise the volume? It's a little bit low.
This presentation will have the following format.
Dr. Henry, I think that's the highest I can go with it. All my volume is up.
Background, literature review,
Okay, Chuck, we can keep going.
problem and proposal, research method, results, recommendations, and conclusion. The energy cost in the Caribbean is the highest in the Western Hemisphere, and it's amongst the highest in the world. Caribbean countries, with the exception of Belize and Trinidad and Tobago, are dependent on imported petroleum to meet the energy demands of the population. Many Caribbean countries have had to purchase petroleum externally, which means there is no long-term energy security, and they can experience unstable oil prices as a result. So, ocean thermal energy technology comes in because the sun releases massive amounts of irradiation daily, and this radiation, or some of the radiation, is equivalent to around 200 billion barrels of oil. And on the daylight, the temperature of the surface of the water ranges from 25 to 29 degrees Celsius, and at depths of 1,000 meters to temperatures of 7 to 6 degrees Celsius. Ocean thermal energy conversion is a system that uses the temperature differences that exist between deep and shallow waters to run a heat engine. The temperature difference needs to exceed a specific amount, and this can only be found in certain waters, and the tropics is one of them. The temperature of the surface of the water is enough to boil the working fluid, and then the cold water from approximately 1,000 meters deep is used to condense the working fluid by pumping it to the surface. There are several countries in the Caribbean with the potential for OTEC. Just to name a few, we have Jamaica and Cuba in the Greater Antilles, and Martinique and St. Lucia in the Lesser Antilles. OTEC is relevant to Jamaica and the region because of its location, energy demand, water issues, and ability to attract large foreign investors. Now, this is not only true for Jamaica, the potential exists in other Caribbean countries as well. In this table to the right, you can see, just to name a few countries, Bahamas, Turks and Caicos, Haiti, Dominican Republic, etc. The best sites for implementation in Jamaica are the west and northwest of Jamaica. It can be confirmed based on that map of Jamaica. You can see the bathymetric contours as well as the depths closest to the coast. The problem is that OTEC is costly, which makes it unattractive to investors, and there are environmental hazards associated with closed cycle OTEC in particular. The proposal is to use thermoelectric OTEC, shortened as TE-OTEC. This is a simple system that uses a thin layer solid-state generator rather than a working fluid such as ammonia, which is used in closed-cycle OTEC. That means that it has no evaporator, no condenser, no pressure vessel, or thermogenerator. You can see the comparison in this diagram here. And so thermoelectric OTEC only has a compact heat exchanger to transmit heat through the thermoelectric generator. Thermoelectric theory refers to the Peltier and the Seebeck effect, but specifically the Seebeck effect as it relates to producing electricity from heating. Using the application TGDS, we were able to simulate and analyze the performance of a thermoelectric generator for various materials. The simulation focuses on specifically the performance of N and P-type bismuth telluride, silicon germanium, and magnesium 2 silicate, as well as higher manganese silicate. The best material is determined based on the thermal conductivity, the Seebeck coefficient, and electrical conductivity as a function of temperature. The results from the simulation are relevant to determining the most efficient material for thermoelectric OTEC. This shows that the results of the simulation, based on the thermoelectric properties stated before, are ideally we want a high Seebeck coefficient, a high electrical conductivity, and a low thermal conductivity, and this is why. The Seebeck coefficient as high as possible means that we've maximized energy conversion, as Seebeck coefficient is a parameter that links input temperature difference to output voltage difference. That means that we've maximized energy conversion. Electrical conductivity as high as possible will reduce joule heating due to internal electrical losses, and thermal conductivity as low as possible will maintain heat at the junctions and minimize thermal losses through the thermoelectric material. from the simulation, we can also get the maximum power and the maximum efficiency from each thermoelectric material. Based on all the results, it was determined that the Discussants 2 telluride was the most suitable for material for the thermoelectric generator. The recommendations are that firstly, thermoelectric OTEC does not share any of the hazards of closed cycle OTEC and is generally safer for employees and the environment alike. Through proper site selection, the materials used, the construction technique, we can minimize environmental impact and substantial costs associated with it. Additionally, the research found that using 2 or more renewable energy technologies to improve the system is beneficial to all involved, including consumers. So using solar energy collectors can improve the thermodynamic efficiency of OTEC. In conclusion, OTEC can serve Jamaica and really the Caribbean by establishing energy freedom and producing our own energy. It is costly, but it has a higher annual power output than most other sources of energy, most common to Jamaica. The byproducts also make it attractive. Thermoelectric OTEC is the most ideal form of OTEC because it uses less materials and that would require less labor and time to install. Thermoelectric materials improve the performance, and N-type bismuth telluride is preferred when all the coefficients, maximum power, and maximum efficiency are considered. These are my references. Thank you for listening.
Okay, great. And that was right on time. So she did good with the timing. We're gonna jump straight to our next presenter, who is Dudley Williams, although I don't see Dudley Williams on the. Oh, I see Dudley Williams now. Okay, great. All right, so let me just do a quick intro. Dudley Williams is an adjunct lecturer at the University of West Indies Mona campus, where he teaches classical physics, renewable energy, and IT. Mr. Williams is currently pursuing a PhD in applied physics, intending to research alternative cooling methods to solve the issues faced by warming in the Caribbean. He holds a Bachelor of Science in Alternative Energy and a minor in Computer Science, and an MPhil in Applied Physics from UWI Mona. He's worked on energy projects for the Barbados, Secret, and Antigua and Barbuda's Department of Environment. So he's been around the Caribbean region doing work. Today, he is going to present on the Caribbean building sector resilient to extreme wind, not temperature, an assessment of the thermal performance of the current and potential green cooling technologies for the Caribbean region. So I'm gonna hand over to Dudley and ask him to present.
Good morning. Thank you for the introduction. So as mentioned before, my name is Dudley Williams, and the title of my presentation is The Caribbean Building Sector, Resilient to Extreme Wind, Not Temperature, an assessment of the thermal performance of current and potential green cooling technologies. My supervisors are Dr. Ferrat and Dr. Dorville. Now, this is the outline of my presentation, and I will jump straight into the background. So achieving thermal comfort. Why do we need cooling? What is thermal comfort and how to achieve it? Now, why do we need cooling? The human body constantly exchanges heat with the environment, and therefore temperature regulation is a homeostatic feedback control that ensures core body temperature